So I'd like to introduce you to the concept of a mean and an expectation. In order to explain this, I'm going to bring back our dartboard and an axis. On this particular dartboard, the maximum score we can get is 3. Now remember, this dartboard forms a sample space of all the possible positions that we could land a dart. Imagine somebody just took 2 shots at this dartboard, at the positions shown. As we know, a random variable can take an element in the set of positions and map it directly to a real number. Let's go ahead and do that for this particular example. Just to remind you how this works, this particular point is at the position 1, -1. So we can sub that into the random variable, which is just a function. We can see that its output is just this real number 3, which is what we got here. Let's go ahead and remove these arrows in this working out, because it's just going to get in our way. Now you're going to start to see why this random variable is useful. Because we have these numerical outputs, we can go ahead and do math with the numbers, and we're very good at doing math with numbers. The simplest value we can define is the mean. The mean of this little v we can write down with a hat over the top. In simple terms, we can say that the mean is the average number of points we got per shot. In order to explain this, let's try to think about these 2 particular shots that I've drawn. We can see that we've got 4 points in total with these 2 shots. However, we can say that we've taken 2 shots, so instead of writing this as 4, we can say it's 2 times the average. We can go ahead and solve for the average just by dividing by 2. If we go ahead and calculate this, we can see that this just evaluates to 2. We can go ahead and draw the mean directly onto the random variable's axis. I've drawn this as a triangle because I want you to think about it in a particular way. If you think of this whole structure like a seesaw, then 2 is where you'd have to put the hinge so that the seesaw doesn't tip over. I'll go ahead and get rid of the calculation we've done so far. Now, what if somebody came along and took another shot, and it also landed on 3? In order to demonstrate this, I'll go ahead and add this shot directly to the random variable axis. Now you can see that there's twice as much weight on this side, so the whole thing looks like it wants to just tip over this way. So intuitively, you'd want to move this thing over to the right in order to compensate for the extra weight on this side. Working this out mathematically, the scores we have are, and we've taken 3 shots, which we want to replace with the new mean. We can go ahead and solve this as well. If we plug this into our calculator, we can see that the new mean is just 2.3 repeating. So as we would expect, this pivot point moves to the right just a little bit. And now the whole system is balanced again. Now we wonder what might happen if this person just keeps shooting at the dartboard. Imagine he took 10 shots. Because this is starting to get crowded, we don't actually want to keep stacking them like this. So instead, what I'm going to do is I'm going to draw on a frequency table. I'll also get rid of the old mean for now. Now we can go ahead and fill in the frequencies directly. Now let's make sure we know how to read this table properly. If we look at the value of 1, it says that 4 shots have landed inside of it. Let's look at the set on the left. As expected, there are exactly 4 shots inside. Okay, let's get rid of all of these markings. And also, the values over here are outdated too, so let's get rid of them as well. Now we can just blindly go ahead and calculate the mean the exact same way. Now we could go ahead and put this into the calculator directly, but I'm going to show you a few simplifications that will make your life a lot easier. As you can see, these values are repeated, so why don't we just go ahead and use multiplication to simplify them? What we're saying here is that we have 3 zeros, 4 ones, 1 2, and 2 3s. We also know that we can break up fractions when we have pluses like this, so let's go ahead and do that as well. Now if we put all of this into the calculator, we go ahead and find that the value is just 1.2. I'm going to give you a useful analogy. I want you to look at these numbers. I hope you can see that they add up to 1. I want you to imagine you had a 1 kilogram object broken up into 10 parts. I want you to imagine that 3/10 of a kilogram went to 0, 4/10 went to 1, 1/10 went to 2, and 2/10 went to 3. Now if you imagine this whole thing like a seesaw again, we're saying that if you put the lever at 1.2, it's not going to tip over. This makes sense again because you're putting the lever closer to the heavy masses to avoid them falling over. Now let's get rid of this all one more time. Now let's imagine them taking 1,000 shots. It's going to take me way too long to draw all of these, but I'll just draw a few to fake it. Okay, well that's quite enough of that. Now I want you to imagine that I actually did sit down and count all their shots, and I gave you the following frequencies. Again, we can calculate the mean in the exact same way we did before. We can say that 284 out of the 1,000 shots landed on 0. And we can repeat this for all the other values as well. If we put this into our calculator, we just get 1.236. Again, you can just imagine having a block that weighs a kilogram and distributing its mass across all of these places. Now just like before, we know that we should put the balancing point right here. Again, this is closer to the heavier parts so that the thing doesn't tip over. Now as you can see, if this thing weighs 1 kilogram, this is sort of similar to the way that the probability of a sample space is always equal to 1. If I just get rid of this estimate for now, and move my box over to the side, we know that after lots of trials, these values are just going to approach the true probabilities. We can see that this value is just going to approach what the PMF gives us for 0. And this value should just approach what we'd get for 1. We also know that if we repeat this experiment 1,000 times, the mean we're eventually going to approach isn't ever really going to change. Now I've been giving you frequencies, but I want you to imagine that we actually had the true probability that this person would hit each particular value. Now given these probabilities, it's actually possible to calculate the expected value directly, and the way we do that is just inspired by this formula, as I'm about to show you. As you can see, this particular value is similar to the probability of getting a 0. We then just multiply it by 0. This value is just like the probability of getting a 1, and we just multiply it by 1. If we go ahead and do this for these particular probabilities that I've got, and put this into a calculator, we get the value of 1.25. This is very similar to the value we got when we were actually just throwing darts many times. Now remember, we can take this position L and use the random variable to map it directly to this axis here. I also want you to remember that the probability mass function just takes this value and maps it directly to a probability. Now because of this, we say that this random variable determines this expected value directly, so we have another notation that makes this a lot clearer. To work out this expected variable, take every possible output value and multiply it directly by its probability, and then sum them all up. Let's go ahead and write down the definition of this expected value. One final thing to say is, if we cleared all the actual shots that this person took, if I told you to guess where their next shot would land without any other information, your best guess should be just 1.25. Now this is a bit strange because there is no 1.25 on the dartboard. You can either get a 1 or a 2. But as we said, after many shots, the average that this person will reach is just 1.25. So in summary, the mean is just the average value you would get per shot if you haven't taken that many shots, and the expected value is the value that the mean approaches after you've taken many shots.